We did some trigonometry to find the instantaneous center of rotation, and then we found the derivative of state, and we integrated to find the change in x, change in y, change in t, right? So if you go back to my lecture from last Friday, we kind of covered this in detail. So and this is going to give us our dynamic model, right? You integrate these things, you add a bit of noise to the inputs and the outputs, and that gives you your motion model. The second part of the Bayesian filter is the measurement model, right? So what we did is we said we're going to have k different measurements, z1 to zk, and we're going to assume that they're conditionally independent, right? So which means that like you can decompose this joint probability of k different things into the product of individual z's, and each of those z's correspond to a single beam, right? So this is a single beam LiDAR model, and then we like went into the details of the 4 different types of measurements you could have. So just to recap, you have like a little bit of Gaussian. This is the true distance, ZTK star, right? So you can say that this is your true distance, and around your true distance, you have like a Gaussian peak. You have like likelihood of unexpected obstacles. You have sensor failure, and then you have like random noise, right? So the 4 types of failures, you can just kind of see it from this this really weird looking probability distribution, right? But you can see that like there's a little bit of Gaussian on the true accident. There's some probability that you didn't model some obstacles. There's a little bit of likelihood that you completely had sensor failure, the beam didn't come back, and there's some likelihood of just like uniform failures, right? And so your sensor model is going to be a combination of those 4 likelihoods. You want these things to sum up to 1 so that you have a proper probability distribution, right? That's it. And how did we invent this model? We invented this model by like looking at how LiDARs actually behave. So like a bunch of people like went and like ran LiDARs a bunch in the real world and saw how they actually behaved. And this is a model of how LiDARs work. Now the true model is going to be a little bit different, but that's why it's probabilistic, right? Like that's why it's a probability. So if you look at this particular formula, right? Like there's these 4 numbers, z hit, z short, z max, and z ran, these weights. And often the hard part of tuning a sensor model is like figuring out what these weights are, right? And so let's get through this. But the typical practice here, you do it either offline or online, but you just kind of have to collect a bunch of data where you know the ground truth, right? So imagine that you were in a motion capture cage, you knew exactly where you were, or you like recorded by hand, but then you record what the LiDAR does, and then you try to like fit the parameters of those 4 different Z values, like Z hit, Z short, Z max, and Z ran, that best explain the data that you actually see, right? So when you want to like fit this offline, you're essentially going to have a true X. You're going to collect a bunch of Z's, right? And then you're going to try and find the like Z hit, Z ran, Z obstacle, whatever, those 4 numbers, so that the like likelihood of P of Z given X with those parameters, let's call these parameters, let's say theta, is like maximized, right? So you try to say like, let's choose the parameters which maximize the likelihood of the actual data that you see. And so this is what you'd often call maximum likelihood estimation, right? So you're saying that like the likelihood of getting Z, like when I choose the parameter theta, the likelihood of getting the reading Z when I'm at the true X is P of Z given X theta. And I want to maximize the likelihood. I want to choose the thetas which maximize the likelihood of the actual data that I've got. And so you can do this offline, but you can also do this online. So the online way of doing it is a little more vibe checky. But basically, you can simulate a sensor reading at one spot, and then like move the X around. So like simulate a sensor reading, let's say like at this spot, right? So you get this particular sensor reading, and then like move the X around and like plot what P of Z given X is at different X's, right? So there's like what you should have is like a peak around the true position, and then you should have it kind of fall off at positions around there. So if you set the readings wrong, you'll have like spikes in different places, and you can often like tune the parameters so it looks sensible. Like really, when you say it looks sensible, you want to have like, let's say this was the real position, you want to have like a lot of likelihood there, and then like a little bit of likelihood spread out to other positions. So you want to maintain some uncertainty, but what you really don't want is like something that's uniform everywhere, right? Like, because that's uninformative. And so in your homework, you're gonna have a little bit of tuning of your parameters, but like the ways you can do it is through either maximum likelihood offline, or you could do it through online plotting of for a particular sensor reading, see what the likelihood is at different x's, and you want the like likelihood function to disambiguate where you are. Right? The whole point of the likelihood function is to give you information about where you are. But if it's just flat, it doesn't give you information. Okay, so putting the pieces together, this is how the LiDAR algorithm would work. If you ever want to compute the measurement model, that you want to compute P of Z given X to use in your Bayesian filter, you raycast for many different rays which point in different directions. You compute that like likelihood function that looks like that for each beam, and then you multiply them together across all the beams, right? And that's going to be how you compute the measurement model P of Z given X for any of your Bayesian filters, right? So the motion model, as we talked about, is going to be you just do this trigonometry, right? You just do this trigonometry, you just code it up, add a little bit of Gaussian noise to the actions and the outputs. And for the measurement model, you're just going to take your Z given X, you're going to stick it with these things, you have to set the set of weights, and then you can get P of Z given X, and you run the Bayesian filter. So what we're going to talk about for most of today is how to instantiate a practical Bayesian filter. Okay. So one of the challenges with Bayesian filters is this assumption of conditional independence, right? So you say that like all the beams are conditionally independent, but if you have two beams that are too close by, they're not conditionally independent. And a challenge when you have something that is not conditionally independent, but you assume that it's conditionally independent, is that you double count. It's like if this and this are like representing the same thing, but they're not independent, if you just multiply them, you're double counting. And so one way to deal with this like overconfidence, like the simplest thing is to like keep LiDAR beams further away, right? But another way to deal with it is to just like weight this by an alpha, right? So you're like gonna say like every likelihood, I don't let it have like its full contribution. I just weight it by an alpha where alpha is less than 1, right? And so I'm gonna multiply a bunch of like P of Z's for single beams. I'm just gonna like weight them by alpha. Like, so if you weight them by like alpha at 0.5 or 0.9 or whatever, you're not letting there be as much double counting, right? And so that's how you're going to deal with overconfidence. So if you ever find in your homework that your sensor model is not behaving as you'd expect, try these kinds of things, right? Try adjusting the parameters, try downweighting things with an alpha less than 1. Any questions? Thoughts? Feel good about the observation and motion model, right? So that's going to be the first part of our class today, but really what we're going to talk about is the particle filter. And it's like the thing you're going to implement. It's a super cool algorithm. Very simple, but it takes a little bit of getting used to it. So what is a particle filter, right? We've been talking about Bayesian filters in the abstract. We've said there's like this entity of belief, and then there's this belief propagation and these sums and these normalization things, but it's still like very abstract, right? Like it's not something I can implement in code. And so the simplest way of doing this is through something that is like discrete, right? So if I like, for instance, had X, Y, and theta, if I took my state and I discretized it, I just binned it, right? Imagine I had X, Y, and theta, and I took X and I just like binned it. I took Y and I just binned it. I took theta and I just binned it, right? It's my ugly version of it then. But the nice thing about binning it is you can convert any continuous problem into a discrete problem, right? And so once I have a discrete problem, what I can do is take each dimension and discretize into k different bins, right? Like you just like divide it into k different bins, and then you just do like np.floor, right, to put it into each bin. Now, if I have k bins per dimension, what's the problem with that? Like what what happens if I have k bins per dimension? Or should I just do that? That's what do you think? Lots of bins. Yeah. You have k cube bins, right? Now imagine your state was a 42-dimensional humanoid and you had 100 bins per dimension. Now you have 100 to the 42 bins, which is computation quickly becomes intractable, right? And so the reason to do bins is like if we need to compute the first option to do a data structure to implement the belief state is that beliefs are just like tables, right? They're just tables over discrete values. But if I want to do something that's a table over discrete values when the true state is actually this multi-dimensional continuous vector, the challenge is that your bins quickly blow up, right? And you get cursive dimensionality. And so like you have exponentially expensive memory, and as a result, you'll have exponentially expensive compute, right? And so if you're running a car at like 100 hertz, you can't do that. Okay, so the thing to notice here is that like the car is in one spot, right? Like it's in one spot and there'll be some uncertainty around it. A lot of the bins are empty, right? So if it's like if I look at like a k by k by k by k, matrix or whatever tensor of discretization, right? Like a lot of these bins, you kind of think in each of these boxes, right? The car is going to be there'll be some probability in a few of them, but a lot of the entries will be zero, right? And so if I think about discretizing a multi-dimensional vector, in this case, like there's like special structure, there's sparsity to the problem, right? It's not just like every bin is full. And so the trick to particle filtering is to leverage that sparsity. It's to leverage the fact that many of the bins will be empty. All right. So the key idea in particle filters is instead of representing every bin, right? So if I like the idea of discretization is that I have k per dimension, k to the n bins. Let's not represent all the bins. Let's only represent the bins that have some probability in them, or let's only represent things that have likelihoods, right? So let's say there was some likelihood here and here and here and here and here, right? I don't need to keep all the bins around. I just need to keep like this. I need to keep track of this and this and this and this and this, right? And so the idea behind particle filtering is that you just represent belief, not by a table of bins. Sorry. Not by a table of bins, but rather by a set of particles, right? And the set of particles denote like your probability distribution. And so if you let's look at this particular list, right? It has like S1, S1, S2, S10, S40, 40, 40, 55, 55, right? And so it's saying that um, there's like some likelihood at S1, less likelihood at S2, less likelihood at S10, a lot more likelihood at S40, and some likelihood at S55, right? And so the probability of a particular state is kind of like how many instances of particles exist at that state, right? So the more particles that exist, the more probability there is. Right? But you're saying that like the belief state is not some table or some Gaussian or anything like that. It is just a list of particles. And particles are like states, right? Like particles are exactly states. So these are like states, and we're saying that like in our belief, we think that there's way more likelihood of 40, and then there's some likelihood of 1 and 55, and then there's less likelihood of 2 and 10, right? And so we essentially are going to keep a data structure, which is a list of states, and then we're going to like manipulate this list of states and move them around through our motion model and our observation model. Right? But the trick is that you're not going to represent a table, you're going to represent a list of states. And that's going to be your belief state, right? And we're not saying that the state is any one of these things. We're saying the state is a belief over all of these things. Right? And like the number of occurrences of a state denotes how confident you are that it's in that state. Right? Okay. It's a little bit weird as a concept, but basically you're like leveraging the fact that you can kind of think of this as like you're only keeping track of things where there's probability. You're not keeping track of any of the empty bins, right? And you're putting more particles where there's more probability and less particles where there's less probability. That's it. Questions? Yeah. So often you'll choose a fixed set of particles, but you can always inject more particles. So it doesn't have to be a success. So one of the cool things that one of the papers we'll discuss is depending on how confident you are, you can like reduce the number of particles you have. So your model can get faster in case of very confident. So when you have a high uncertainty, you have to have more particles because you have to represent more probabilities in different places. But if it's in like, I'm at S1, I don't need that many particles. Okay. Yeah, there's going to be like, there's going to be a mechanism for resampling that we'll talk about, which will allow for yes. Good question. Okay. But the nice thing is now, if I think about the like compute and memory for this data structure, it doesn't scale with k to the n, right? It's like leveraging the fact that most of the time your belief is going to be much less high dimensional than that. Okay, so this seems like I just like introduced a construct, right? I introduced this construct of like representing belief as a set of particles, but it seems a little arbitrary, right? So like, can we do all of the operations of Bayesian filter with this representation of belief, right? So far what we've done is we've said, okay, we're going to take our Bayesian filter. We like wrote down the observation model, LiDAR model. We wrote down the motion model, which is the kinematic bicycle model. And now what we're trying to do is we're trying to instantiate what is belief, right? So let's kind of go back to the Bayesian filter and see if the particle filter kind of lets us instantiate a Bayesian filter. Okay. Alrighty. So in like the important thing to think about is if you look at the Bayesian filter, like the main operations, like this integral in continuous space this sum in continuous space becomes an integral, right? And this normalization term becomes a 1 over integral, right? Like a normalized term. And so we need to just make sure that like those integrals and 1 over integrals can be evaluated with these particles. So, a graphical way of looking at this is that imagine that is my probability distribution, or that's my belief, right? The thing on the left. If that's my belief, you can kind of think of the particles that represent that belief looking something like this, right? There's like some particles here, a little less particles here, more particles here, a lot of particles here, and then like, you can see that as you add more and more and more particles, this belief becomes more and more accurate, right? And so there's some trade-off, I think, as Isaac was getting to, of like how many particles you want versus like how accurate your belief needs to be. Like the more particles you have, the more accurate your belief will be, but it becomes computationally effective. And so often the trick in particle filtering is choosing just enough particles that will represent your belief, but also be computationally tracked. Okay. So let's think about what we actually want to do with the belief. Right? We don't care about the belief just to care about the belief. We often care about the belief in order to make decisions, right? So for instance, if I had a belief over a state, right? I will often want to say that I will want to make decisions that are good in expectation over the belief, right? So it's like, hey, my car could be here or here or here or here or here, and I want to make a decision that's good in expectation over that belief. Right? I want to say something that's good in average. And so one of the key constructs we need to do with particles is compute an expectation. And so an expectation, just by definition, expectation of f with respect to some probability distribution P is an integral f of x, P of x dx, right? So what we want to be able to do is with the representation of belief as a set of particles, can we actually compute expectations, right? Expectations are just averages, right? Just averages. And so the reason to do this is if you want to do something like get my average position, I want to make a decision which is good and average. I want to get my average probability of collision. In the next module, you're going to learn about planning, right? You want to do planning under uncertainty. So you want to take like either the expected or the worst case planning bound under uncertainty, right? And so in most of these cases, you want to compute the expectation. The nice thing about particles is that it really affords an easy way of computing an expectation, right? And so this is an idea called Monte Carlo estimation. Have you guys heard about Monte Carlo estimation? And Monte Carlo is a famous gambling spot in Europe, right? And like the idea of Monte Carlo estimation is very simple. It's just basically like estimate expectations with samples. Like estimate integrals. If I want to get an expectation, that's like this is like the key tenet of Monte Carlo estimation. It is saying like if I have an integral with respect to a probability distribution, I can approximate that integral by just drawing a bunch of samples from that probability distribution and like averaging them, right? And so the key idea of Monte Carlo estimation is replacing integrals with samples. It's like replacing closed form likelihoods with compute. It's like compute the shit out of everything. And that's the key, right? And so the idea is that if I have a belief, right? If I have some probability distribution, I'm taking the expectation with respect to. All I need to do is draw a bunch of samples from that belief, evaluate F at each of those samples and average, right? And what the Monte Carlo like estimation tells you is that in the limit of n tending to infinity, it'll give you the correct expectation, right? And so often, like when you hear about unbiased estimators and stuff like that, it is like asking whether the Monte Carlo estimate, like you draw a bunch of samples and average, gives you the same thing as the true expectation. So the nice thing is that if I have a belief that is just a set of particles, I can compute the expectation in a really easy way. I just need to like take all my particles. I need to evaluate F at each of those particles, and I just need to average. Like I don't need to do any, like I don't need to actually know the likelihood. If I knew the samples, like if I had a bunch of samples, basically, I don't know belief. I just have a set of particles that represent belief, right? You can kind of think of those particles as samples from belief, right? If I have more samples, that means I have higher probability. Less samples, that means I have lower probability. And so the idea here is that if I ever want to compute the average, I just take my list of particles, right? S1, S1, S50, S40, whatever. And then I just evaluate F at each of them, and then I average. That's it, right? And so particles let you compute expectation really easily. Yeah, so like I kept F abstract here, but F could be things like, for instance, if F was your position, right? Like if F was like X, then expectation F is your average position. Or if F was like the probability that your current position is in collision, it is the average likelihood that you're in collision. Right? So whenever you're probabilistic, you want to often take the expectation so that you can like make a good decision on average. And so that's the idea. Like it's abstract on purpose, so that you can plug in whatever. Right. So I think we'll talk about the particular choice of F in planning and control. But like for instance, often the F you'll choose is like the cost to go, which is saying that like if I was at X and I took this decision, like how bad would it be or how good would it be? And then you want to say like what is the average goodness of a particular decision? And then you like you choose a decision based on how good it is on it. Any other questions? Okay, so what do? We said that we don't want to represent lots of bins. We're just going to represent a set of particles. More particles means higher likelihood, less particles means lower likelihood. And we are going to be able to compute expectations by just taking each of those particles, evaluating F at each particle and averaging, right? Good. All right. So an example here is kind of fun, which is you want to estimate the area of a circle. Of course, you could use like pi r squared, right? But another way of doing it is to just draw a circle and then just like just draw random things in that unit square. and then see what is the probability that it lies inside the unit square, right? So you can like estimate the area of a circle Monte Carlo, right? So you could of course use the formula to do it, but you could also just say, this is my shape. I'm going to like draw samples at different places. I'm going to give it a 1 if it's in the circle, and if it's 0 if it's outside of the circle, right? And if you look at the average of that indicator variable over many, many, many samples, it will give you pi over 4, right? And so the interesting thing, just like the useful tidbit outside of this class as well, is just like, if you ever have like a nasty probability distribution, just like sample a lot, right? And so there's like a lot of nice techniques called MCMC, Markov chain Monte Carlo, which like really, build on the principle of sampling. They're just saying like, I don't know how to like integrate the probability distribution that's nasty, just like sample a bunch and take the average. So it kind of looks like this. Now, you should never do this to estimate the area of a circle, but in other cases, it makes sense. In cases where it's like really hard to evaluate it's really hard to integrate the probability distribution. So examples that often come to mind are like scientific applications, like when you're doing things in like, nuclear physics or chemistry. Like those experiments are expensive, and they're like really hard to like get a closed form for. So often you'll use like a Monte Carlo method. And so these big like supercomputers are just running Monte Carlo in some way. Okay, so let's connect this back to what we care about, right? We care about state estimation. Right? So we care about going from belief at xt minus 1 to belief at xt, right? And so this is the like integral version of what we've been talking about. This is belief at xt minus 1. This is the motion model, right? If you remember, it is like a sum pxt given xt minus 1 ut belief xt minus 1. Like this is just the integral version of that. And this is what we'd call belief bar, right? And then this is our measurement model, right? So we're going to take our belief bar, we're going to multiply it by P of ZT given XT, and then we're going to like normalize, right? So we're going to like normalize by like one over the integral, right? So we're going to like omit that because it's a handful to deal with on your slide, but this is exactly the same as the Bayesian filter, just the like continuous version of the Bayesian filter, right? Belief bar and belief. We are just going to try and work through the math of like what happens if I represent belief xt and belief xt minus 1 as a set of particles, a set of states, list of states. So what we're going to try and figure out is if I have some list of states at xt minus 1, how do I change that list of states at xt, right? So the belief is just your list of states, and our manipulation is going to be how do we change the list of states from one time to the next. Like so something in the states or their occurrence or their frequency will change, right? But I'm just going to try and make that data structure, which is the list of states, is that data structure, which is the list of states at the next step. Okay, and the intuition, if you ever get confused about Bayesian filters, it's like higher likelihood means more particles, right? Like when you're looking at your homework, you think the car is here, it should have the most particles. Right? And so it's like really nice and easy to visualize because you just like plot all your particles and you see where they are. So it's like a visualization again, you have like lots of particles here, and then they kind of taper off as you go further. Okay, so how are we doing on time? Okay. So we are going to try and instantiate the dynamics update, the motion update, and the measurement update, both with particles. And the questions we're going to try and answer is like, this is often called marginalization, right? When you're integrating out the xt minus 1 variable. How are we going to do that with particles? And then how are we going to do the normalization with particles, right? And like those are the two questions we're going to ask. Right. So it's not when it's a probability distribution like a table, this is super easy. You just like do a sum and you just like renormalize over a column, right? But when it's like a list of particles, it's not as obvious how to do it. Okay. Does it make sense? Everyone with me? Ish. Okay. Let's recap. Let's recap. Just to make sure we're on the same page. So we started with discretization a scale with k to the n. Instead, we're only going to represent things that are not empty, right? So we're going to have a list of particles, which is a list of states. You can kind of think of the graphical representation there. The nice thing about a list of states is it allows you to estimate averages. You just evaluate everything in that list of states and take the average, it gives you the expectation. And all we have talked about so far is revisiting the Bayesian filter and just representing everything as a list of states. That's it. Right? Okay. So I haven't actually told you anything yet about how to actually do it. So let's talk about that. Okay, I'm going to go a little fast because we do have to finish the particle filter, otherwise we can't do our quiz and stuff. But let's start by thinking about the motion step, right? So the motion step is, say you have belief at xt minus 1, and you want to propagate belief at xt minus 1 of the belief bar. Right? The belief bar is, say, you integrate the latest action, but not the latest measurement, right? And so the only difference from everything we've talked about so far is this integral rather than the sum, right? So the dynamic step, the motion step in particle filter is really easy, right? What we're actually going to do is something that's really simple. Let me actually fast forward and then I'll come back. So the practical instantiation of the motion step for particle filter is that you actually just take each particle, you pretend that is the true state, you push it forward through your dynamics model, and then that gives you the next particle at belief bar, right? So imagine that your belief at time step t was this set of particles, right? Like the way to propagate it to the next time step is to say, pretend that my state was like exactly this particular state, and then like take my dynamics model, right? This thingy, and like just stick in that value into xt minus 1 and the actual action that I took. And that thing, this like dynamics model will give you like a new state, right? And you just like literally take everything in your list, every single state in your list, and put it into your dynamics model. And when put to your dynamics model, it'll give you a new state. And that is just like your list is just pushed forward through the dynamics model. There's nothing else to it. Right. So imagine this was like S1, S2, S3, S4, S5, right? This thing is going to be like take S1, put it into your dynamics model, draw a sample from your dynamics model. Remember, there's a probability distribution. So you're going to stick in S1 over here. You're going to stick in the actual action that you took. Let's call it U1, or let's call it U maybe, right? And I'm just going to draw a sample from this distribution. So I'm going to say like, let me call it S1 prime. Okay? I'm going to draw a sample. And so I'm just going to like push this thing forward. It's going to give me a state at the next time. I'm going to do the same thing with this. I'm going to do the same thing with this. I'm going to do the same thing with this, right? And so all I've done is like, this is my previous list of states. This is my next list of states, right? So there's no like fancy manipulation. Like all you're doing is taking every single state in your list of belief, right? And you're pushing it forward with the dynamics model. You're drawing a sample, and that new sample is your, like the collection of new samples is your new belief, right? And so you can kind of think of like the intuitive way that I like to think about this is that like, imagine that there was like a lot of particles here, right? Like they had a lot of belief that I was at this state. Like I had a ton of particles right here. What's going to happen is I'm going to draw many samples from here, one for each of these things, right? And so like the same belief will propagate a lot, right? So it's like if I have a lot of samples here, then I'm going to push forward each of these a lot, right? And so similarly, let's say let's go back to our like example here, right? In this case, you can kind of see this thing at the bottom. You remember this example from our Bayesian filter, right? So it's like this example of a robot which is trying to figure out where it is. It's knocking on these doors, right? So our belief currently is this thing. You can see that the belief is still concentrated. Yeah, our belief initially was this uniform thing, right? Like it doesn't know where it is. So just a set of particles all over the place, right? But when you move it to the right and take a measurement, you can see that the particles start like clumping up around here, right? So you can kind of think of it as like, imagine that I had a set of particles. No, I don't know what's up with that. Imagine that I had a set of particles like right here, right? And imagine that I had a set of particles right here, and then I went to the right. Okay. So I'm going to take each of these particles and stick it through the dynamics model. And so the dynamics model is going to say, oh, well, if you are at this state, you're probably going to move to the right. If you're at this state, you're probably going to move to the right, but maybe plus a bit of noise. If you're at this state, you're probably going to move to the right. So now, after this step, you'll have a bunch of particles right here, right? And so the easy way to think about it is you're just like moving states around, right? So you have a collection of states, you're doing your dynamic step, and you're moving those states, right? And the reason it's still probabilistic is because you're drawing samples from your dynamics model, right? Um, you're you're like not just saying that I'm going to like, it's not a deterministic function. You're saying I'm going to stick in the state, pretend that was the true state, and then draw a sample from the next time step, right? And so this list of states will be translated to a different list of states with some stochasticity because I'm doing sampling. Like sampling as in I'm like drawing from that probability distribution. Right? So if it is our car, like an example with our car would be, imagine our car was here, right? Imagine we took some action and we had some like belief over the car being here, 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 right? We didn't know exactly where we were. So what'll happen is that for each of these, you just like integrate the dynamics model. So if it is here, the sample will give us this. If it is here, our sample will give us this. If it is here, our sample will give us this. And so now my new belief, my old belief was this, and this is going to be my new belief, right? You just take the list of states and you push it forward. Questions? A little bit, it's a little bit confusing to start, right? But actually, like the motion, like there's no tricks to it. Like the motion model is like super easy in a particle, in that you just literally take all the states, you pretend that was like you pretend when I'm pushing this thing forward, it's like I knew with 100% certainty that I was here. And what would happen if I was like, I knew with 100% certainty I was here, what would happen to my next state, right? And then you do that for every particle. And so the particles that are more likely will have more things pushed forward, the less likely will have less things. So if you go back to this example, right? If I have like a lot of particles here and I move to the right, I'll have a lot of particles here. And if I only have a little bit of particles here, I'll only have a little bit of particles. Okay? And so the whole belief distribution kind of moves. But the important thing in the motion step is that the states actually change. Like you're changing, like the numbers in the states will actually change because you're putting them forward to the model. Yeah. From distribution, which distribution? Like the motion model, the P of xt given ut minus 1 and x minus, or ut x. So the car motion model that we had. So like as if you remember what we did in the car, it's like you compute the trigonometry functions and then you add a bit of noise to it. And so you would like pretend your car was somewhere, you would integrate it forward and then you'd add a bit of noise. Oh. Okay. Questions? Okay, maybe let's do a pulse check. Did that make like if that made sense to you, raise your hand. Otherwise, we'll go over it in more detail. More or less? Okay. If it didn't make sense to you, come talk to me after the class and we'll go over it in more detail, right? But maybe the operative fact that we should take away from this is just to move the particle forward. Take every particle, stick it into your dynamics model, that like car model we had, push it forward. It'll give you a new proposed position for the car. That list of new positions is your dynamics update. That's it. Okay. The measurement update is a little more unusual for the particle filter, right? So the measurement update tries to take our belief bar, right? Let's call this thing our belief bar, is the thing we computed the previous step, right? And it tries to say if I have a belief bar and I have a measurement model, how do I like compute this like, sorry. Um, Hmm. Sorry, I lost my iPad for a second. Um, aha, good. Sorry. Um, so yeah, the measurement update says, okay, I have belief bar. I've computed a list of particles, right? Now I get a measurement, right? So I have a list of particles of, S1, S40, S55, things that where I think I am. And then I got a measurement. I got some like Z, right? I got Z0. Now I want to figure out how to change that list of particles given a measurement, right? So the motion model said you had a list of particles, you take each of those particles, you stick it into the car model, it'll give you a new set of particles, right? So it moves the particles. But if I got a new measurement, Z, how do I actually change that list to incorporate this measurement, right? So how do we think we should do it? Like, it's not super obvious if I have a list of particles, if I got a Z, how do I change the part? Right? Because if you remember the intuition for the measurement step, it's like saying if you have belief bar, you like reweight. You reweight that belief bar by the P of Z to give next T, and then you renormalize. But like I don't have any probabilities anymore. I just have a list of particles. So if I don't have a probability, what does it mean to reweight? Right? It's just like a weird concept. So how do we integrate measurement into a particle filter? Okay, so you could try to see like what is P of Z given X maybe, and like try to move a particle to the most likely X given a particular Z. So like something like that. Like try to find an X which is most likely, something like that, right? Like one of the tricky things with doing that is that you like collapse your belief because you're sending everything to the most likely. Right? So if you like, I want to maintain uncertainty, but if I do that, then it'll like everything will collapse to the like the thing that gives me like if I have a Gaussian, everything will collapse to the mean because that's the highest probability. Right? And I'm taking the max. And so one tricky thing is like here, the nice thing about like multiplying and renormalizing is it increases the likelihood, but doesn't send it to like the max. Whereas if I do this, it like collapses the probability to like just the max, where you want to maintain that uncertainty. Is you want to have some diversity in your particles. So the trick to particle filtering is pretty cute. It's they like modify the data structure. So it's no longer just a list of particles, it's a list of particles and weights. And so um, the trick is that you don't just say that I have a list of particles, but I have one weight per particle, right? So it's like if there's like k particles, you have k weights. And so the way to kind of think about it is that like to go from belief bar to belief, right? You can think of this as like a reweighting factor. It's a reweighting factor for everything in belief bar, right? So you're saying belief bar, you like reweight by this P of Z by a normalizing factor, right? And so if I can just add a weight, if I can just add a weight to every particle, then all I need to do is reweight based on the measurement, right? I'm not going to move the particles, I'm just going to reweight. And so the idea in the particle filter is that you're going to keep a set of states as as your belief S1, S1, S50, S40, 40, 40, whatever, right? And I'm also going to have like W1, W2, W3, W4, W5, W6, right? It's like for every single particle, I have a weight. And so in the motion step, nothing changes in the weights. The weights, like let's say I moved S1 to S1 prime. I move this to like S1 prime prime. Let's say I move this to something else, like the weights carry forward. Right? So the weights, like the motion model doesn't change the weights. The weights are what they are, right? So the weights start at all like one. Every particle is equally likely. And the motion model just says, I'm going to move the states and I'm going to move the weights accordingly, right? So I'm going to keep the weights the same. So in the motion model, I move the states and I just carry over the weights. They're just the same, right? And the cool part is in the measurement update, you're going to not move the states. You're only going to change the weights, right? So, sorry, let's erase this guy. Okay. Okay. So in our motion update, these remain the same. These move with the dynamics model. In our measurement update, these will change. These will remain the same. Right. So what's going to happen is that I'm going to take each of these weights, right, and I'm going to multiply by this factor, right, which is P of Z divided by sum of P of Z, right, which is kind of, if you look at the like belief update, it's kind of the same as this thing, right? If you think of an integral as a sum, right, like it's just saying like things that are like, and the intuitive way to think about this is like, if let's say like S40 was the most likely measurement, right? If S40 is the most likely measurement, um, then the P of Z given X for S40, when X is equal to S40, will be the highest, right? Which means that the weights for S40 will be the highest, right? And so you can kind of think of this as like, if I have something with high weight, that means it has high likelihood, right? So earlier we were just saying like, how many instantiations of S40 do we have? We have 3 instantiations of S40, so it's high likelihood, right? And now what we're going to say is that to understand how likely S40 is, I'm going to sum up all the weights for S40. And so I'm going to say like, imagine these 3 weights were super duper high. That means S40 is super likely, right? But imagine that S40 is repeated 10 times, but like the weight was like 0.00001. That means S40 is not going to be likely. Right? So the difference is that earlier we said we're going to have a list of particles. The number of times the particle exists is how likely it is. Now we're going to say we're going to represent how likely a state is by the sum of weights for that particle. Yeah. And the reason to do that is so that you can incorporate this like this measurement model in the whole, right? Because it's hard to know where to move the particles with a measurement model. So, okay, a lot of information. Let's recap, right? We represent everything with a list of particles. We're going to add something to our data structure, which is a list of weights. The list of weights is going to be computed by, at every step, taking our measurement model. So imagine I had S0, S1, S2, 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 S5, S5, something like that is our belief, right? For each of these, I'm going to compute this number, P of Z given X, right? P of Z given, what is the measurement you got? What is the likelihood of the measurement if you had actually been at that state S0, right? So that'll give me, you know, W1, W2, W3, W4, till W, whatever, okay? And then I like normalize, right? So I say for each of the, I just want the weights to sum up to 1, right? So I'm just going to renormalize. And so when you renormalize, it's going to give you a set of weights. The weights will always sum up to 1, right? And the high things that are more likely will have more weight. And so imagine that like from this list, actually what happened was like S1, the measurement like made S1 super likely, right? So like P of Z given S1 is super high, right? So even though S1 only exists once in this list, its weight is going to be super duper high, right? And because its weight is high, its probability is high. Right? And so the main change is that you're just going to introduce this list of weights. Okay. Yeah.
So are the list is initialized after we get our first measurement?
Mhm.
Oh,
They're just actually they're going to be initialized at your initial belief. So like imagine you had your initial belief being uniform. You'll just have like a list of particles that are uniform, and you'll have weights as 1 to start. And then we have an example in a little bit, and we'll go over like how to propagate the weights. But we probably will only get to that on Friday. But you start the weights off at like all ones, and then you like propagate them with measurements. Okay, cool. I think we're at 9:20, but I will see you guys on Friday. Absolutely.